Welcome. I'm glad you're here. Tonight, we'll travel to the farthest edge of our sun's domain, a place so remote light itself takes hours to arrive. Beyond the orbit of Pluto lies a realm of ice and shadows, where frozen worlds drift through the dark. This is the Kuiper Belt, a frontier that holds the history of the solar system, written in ancient ice. Settle in, and let's follow the trail into this vast, silent expanse. The sun's light fades with distance. Near its warmth, rock and metal remain solid. Water is a restless vapor, and the air hums with heat. But as you move outward, past Mars, past the gentle pull of the asteroid belt, there comes a place where the sun's touch weakens enough for water itself to freeze. This invisible frontier is called the frost line, the boundary in our early solar system where volatile compounds like water, methane, and ammonia could condense into ice. The frost line is not a sharp edge, but a transition zone. It lies where the sun's heat no longer keeps certain substances in gas form. Inside this line, newborn worlds could only gather heavy elements: silicates, iron, nickel. Beyond it, ices joined the mix, giving birth to planets many times more massive than the rocky inner worlds. It is here that the architecture of the solar system changes, a divide between the small, dense terrestrial planets and the vast, gaseous giants. When the solar system was young, it was a swirling disk of dust and gas. The sun had just ignited, and the heat from its newborn fusion pushed energy outward. Closer to this heat, lighter molecules, water, carbon dioxide, methane, could not stay solid. They were driven away or evaporated into the surrounding gas. But beyond a certain distance, the temperature dropped below a critical threshold, and ice crystals could form, drifting among the heavier dust grains. This shift in chemistry was monumental. Inside the frost line, only rock and metal could clump together, limiting the size of planets. That is why Mercury, Venus, Earth, and Mars are small, with solid crusts and metallic cores. Beyond the frost line, the availability of ice meant more building material. Planetesimals there grew quickly, gathering both solids and gas. This is where Jupiter, Saturn, Uranus, and Neptune took shape, their cores swollen with ice and rock, their atmospheres deep and massive. The frost line is often placed around 3 astronomical units from the Sun, about the distance of the asteroid belt. But in the early solar system, it may have shifted inward or outward depending on the Sun's activity and the density of the protoplanetary disk. During the Sun's first million years, it flared violently, heating and cooling the disk in pulses, shifting the frost line's position like a breathing boundary. Beyond this icy threshold, the story of planet formation changes. Water ice, abundant and sticky, helped small grains cling together more effectively. This increased the speed at which planetary embryos formed. Farther still, beyond Neptune's orbit, the temperature was so low that even nitrogen and methane froze solid. Here, in the outermost zones, countless icy bodies formed, each carrying a record of those ancient days. These distant objects, the Kuiper Belt population, are survivors of a time before planets settled into their current orbits. They never grew large enough to become full-fledged planets, and so they remain as frozen relics. Their surfaces are coated in ices that have not melted for over 4 billion years. In their chemical fingerprints, we see the conditions of the solar system's youth. The frost line's influence is not limited to the planets. It also shaped the delivery of water to Earth. The inner solar system was too warm for water ice to survive in bulk during planet formation, so our oceans may have been delivered by asteroids and comets born beyond the frost line. In this way, that invisible boundary helped set the stage for life itself. The physics of the frost line can be imagined like the edge of a shadow, except the shadow is cast by temperature. The distance depends on the balance between the sun's heat and the cooling of space. In the protoplanetary disk, sunlight wasn't the only factor. Heat from colliding particles, radioactivity, and gravitational compression also influenced the temperature gradient. But still, the primary driver was proximity to the sun. Today, the frost line is a frozen echo of a moment in our solar system's past. We cannot see it directly, but we can trace its signature in the distribution of worlds. Every icy moon of Jupiter and Saturn, every frozen comet that arcs inward from the Kuiper Belt, every methane-glazed dwarf planet beyond Neptune, all owe their existence to the chemistry of this invisible border. Beyond the frost line, water is not rare. It is as common as rock. On Earth, water is a precious liquid, dependent on a narrow range of temperatures. Out there, it is a building block as ordinary as stone. This changes the balance of mass. Icy worlds can be large and light, holding vast reserves of frozen material without collapsing under their own weight. In modern astronomy, the frost line has another name, the snow line. It is used not only to describe our own solar system's history, but also as a guide when studying exoplanets. When astronomers look at other stars and their disks of forming planets, they often try to locate the snow line. Its position can tell them where gas giants might form or where icy bodies might accumulate. The frost line also helps explain why Jupiter is where it is. Simulations suggest that Jupiter's core formed just beyond the snow line, where ice-rich material was abundant. Its gravity then influenced the rest of the solar system, scattering objects inward and outward, stirring the asteroid belt, and possibly nudging icy bodies toward Earth. Without the frost line's chemistry, Jupiter might never have reached the size needed to dominate the solar system's architecture. In the Kuiper Belt, the frost line feels like ancient history. It lies far inward from those frozen edges, but its effects reach all the way to the present. Every chunk of ice and rock out there, every dwarf planet's glittering surface, every comet's tail of vapor, all were born in the thermal map the frost line once drew. The concept reaches beyond science into a kind of cosmic storytelling. Imagine the young solar system as a vast plain of dust, lit by the fierce glow of a newborn star. Inside a certain ring, heat keeps the land bare. Rocks roll in the warm air, but no frost clings. Beyond that ring, crystals grow on every grain, making them heavier, stickier, more likely to join and form something new. That is the frost line's gift. It decides which worlds will be barren stone and which will be swollen with ice and gas. As missions probe farther outward, to Pluto, to Arakoth, and beyond, they carry instruments capable of reading the ancient chemistry of these worlds. By comparing these readings with models of the early solar system, astronomers refine their understanding of where the frost line lay and how it shifted. This research is not only about the past, it helps us understand how planetary systems form everywhere in the galaxy. The frost line is, in a way, the first great divide of the solar system. It split our worlds into two families, the inner four, small and dense, and the outer giants, massive and gaseous. And farther still, the icy debris fields, stretching into the Kuiper Belt, hold the memory of that divide. Crossing it, in the early days, was a matter of temperature. Crossing it now is a journey across billions of kilometers, into a region where sunlight is only a distant star. If you stand in the imagination at that ancient boundary, you might see the inner solar system glowing with reflected heat, while beyond, the light dims and the cold deepens. This was not just a change in climate. It was the threshold that determined the fate of worlds. Inside, heat stripped planets of light elements, leaving them solid. Outside, cold preserved the ingredients for giants and comets alike. The Kuiper Belt exists because of that divide. Without it, the far outer solar system might have been empty or uniform. Instead, it is a place of variety. Small, icy rocks, large dwarf planets, contact binaries, and ancient cometary fragments. Each is a chapter of the frost line's legacy. And so, the frost line is not merely a technical concept from planetary science. It is the first frontier. It is the line that told water it could rest as ice, that told methane and ammonia they could settle, that told the giants they could grow. It shaped the map we travel now, billions of years later, as we send our machines and our thoughts beyond Pluto toward the edge of the sun's reach. In the silence beyond the frost line, the Kuiper Belt waits. Its worlds are small, but they carry vast meaning. Their frozen crusts are time capsules, each grain of ice a survivor from the dawn of everything we know. They are the frost line's children, and to understand them, we must first understand the line itself. The story begins in the early 20th century, when astronomers scanned the sky for a phantom world. They called it Planet X, a hypothetical giant whose gravity, they thought, was tugging on Uranus and Neptune, subtly shifting their orbits. Clyde Tombaugh, a young and meticulous observer, was given the task of finding it. Night after night in 1930, he compared pairs of photographic plates taken days apart, looking for any point of light that moved against the fixed backdrop of stars. And then, there it was. A tiny speck shifted slightly between exposures. Tombaugh had discovered Pluto. The headlines erupted. School textbooks gained a new ninth planet. It seemed the solar system's map was complete, its borders drawn. But this was an illusion born of limited vision. For half a century, Pluto kept its crown. Its orbit was eccentric and tilted, sometimes even bringing it closer to the Sun than Neptune. But telescopes revealed little detail. Pluto was small, much smaller than the giants, and for decades astronomers assumed it was a unique oddity, a cold relic that had somehow survived in isolation. Few suspected that Pluto was merely the first visible member of an entire population of frozen bodies. That realization began quietly in the 1990s, when new, more sensitive detectors allowed astronomers to peer deeper into the faint light of the outer solar system. In 1992, David Jewett and Jane Liu announced the discovery of a small, icy object beyond Neptune. Not Pluto, not a comet, but something in between. It was the first detection of what we now call a Kuiper Belt object, or KBO. The implications were immediate. If one such object existed, there were likely many more. And indeed, within a few years, dozens were found, then hundreds. Today, we know there are probably hundreds of thousands of these icy worlds orbiting in a thick disk beyond Neptune, stretching from about 30 to 50 astronomical units from the Sun. Pluto was never alone. It was simply the brightest of its kind. The Kuiper Belt reshaped our view of the solar system. It revealed that the space beyond Neptune is not empty but alive with frozen debris left over from the solar system's birth. These worlds are made of rock, ice, and frozen gases, preserved in deep cold for over 4 billion years. They are time capsules, holding clues to how planets formed, and the discoveries kept coming. In 2005, astronomers found Eris, a world slightly more massive than Pluto, orbiting even farther away. This sparked the great "What is a planet?" debate that led, controversially, to Pluto's reclassification as a dwarf planet. But the change in label did not diminish its importance. If anything, it revealed that Pluto was part of a much larger family of dwarf planets, each with its own story. These icy bodies vary widely in size and character. Some, like Haumea, spin so rapidly that they are stretched into elongated shapes. Others, like Makemake, have bright methane-covered surfaces that reflect the Sun's distant light. Many are locked in orbital resonances with Neptune, their paths stabilized by the giant planet's gravity. It is a quiet but intricate dance. Worlds, circling worlds, bound by invisible rhythms set billions of years ago. This population also blurs the line between comets and planets. The smallest Kuiper Belt objects can be nudged inward by gravitational interactions, becoming the short-period comets we sometimes see from Earth. In this way, the Kuiper Belt is a reservoir, slowly releasing icy visitors into the inner solar system. To explore these realms is to confront the vastness of our own neighborhood. Even the fastest spacecraft take years to reach the belt. NASA's New Horizons probe, launched in 2006, sped past Pluto in 2015, revealing mountains of water ice, smooth plains of nitrogen frost, and hints of subsurface oceans. After its historic flyby, New Horizons continued deeper, visiting another KBO named Arrokoth in 2019, a contact binary shaped like a snowman, reddish from organic compounds, untouched since the dawn of the solar system. Arrokoth's surface told a story of gentle formation. Unlike the violent collisions that shaped the inner planets, objects in the Kuiper Belt seem to have grown slowly, their components merging softly in the low gravity and frigid temperatures. This preservation is what makes the belt so scientifically precious. It is less a graveyard than a frozen archive. Yet, mysteries remain. Some KBOs have highly inclined orbits that suggest they were scattered there by migrating planets in the early solar system. Theories of planetary migration propose that Neptune moved outward, flinging some objects into the belt, while capturing others into stable resonances. This dynamic reshaping may also hint at the existence of an undiscovered massive planet, the so-called Planet 9, lurking far beyond Pluto, shepherding certain orbits into strange alignments. If such a planet exists, it would be many times more massive than Earth, orbiting hundreds of times farther from the Sun. Its detection would again redraw the map, just as Pluto once did. But even without Planet 9, the Kuiper Belt itself is a world unto itself, a slow, silent ballet of frozen matter tracing the outer edge of sunlight. Looking beyond Pluto has also shifted how we think about the solar system's boundaries. The belt may blend into the scattered disk, a region of even more distant and eccentric orbits, and eventually into the Oort cloud, a spherical shell of icy bodies extending perhaps a light year away. In this sense, the solar system has no sharp edge, only a gradual fading of worlds into the interstellar dark. The Kuiper Belt challenges our idea of what a planetary system looks like. Instead of ending with a neat final planet, our system trails off into a frozen wilderness filled with relics and surprises. It is not an empty border, but a frontier rich in history, and perhaps in secrets yet to be found. In the years to come, new telescopes like the Vera C. Rubin Observatory will map the outer solar system in unprecedented detail, discovering thousands of new KBOs. Each will be a new piece in the puzzle, a fragment of the story that began in a swirling disk of dust and gas around a newborn sun. Pluto may no longer be our 9th planet, but its demotion was also a revelation. It was the opening door, the first clue that the solar system is bigger, stranger, and more populated than we dared to imagine. Beyond the 9th planet lies not an empty void, but a vast, shimmering archipelago of worlds, each quietly orbiting, each a frozen chapter in the long history of our cosmic home. Step past Neptune's orbit, and the solar system changes. The light fades, the sun shrinks to a bright star in a black sky, and the realm of the giants gives way to something quieter, but no less grand. This is the Kuiper Belt, a vast, flattened ring of icy bodies stretching from about 30 to 50 astronomical units from the sun. Unlike the empty stretches between the inner planets, here the space is populated, not crowded like a city, but rich enough that in every direction unseen neighbours share the same great highway. For centuries, we imagined the solar system as a tidy sequence of planets, ending abruptly with Pluto. But since the first Kuiper Belt object was confirmed in 1992, our picture has transformed. We now know there may be hundreds of thousands of sizable bodies in this region, and possibly trillions if you count the smallest. It is an entire population, hidden for most of human history, now coming into focus. The scale is staggering. Astronomers estimate that there are at least 100,000 objects over 100 kilometers in diameter orbiting in this belt. That's not counting the countless smaller fragments, boulders, shards, and snowballs, formed from the same ancient materials. Many of the largest are worlds in their own right, with mountains, basins, and possibly subsurface oceans. Pluto, Eris, Haumea, and Makemake are just the most famous examples. The variety is remarkable. Some KBOs are nearly spherical, their gravity strong enough to pull them into rounded shapes. Others are irregular, like giant lumpy asteroids, evidence of a quieter growth process or past collisions. Their colours vary from grey to deep red, depending on their surface ices and the organic compounds, tholins, that form when sunlight and cosmic rays interact with methane and other volatiles. Despite the poetic term sea, this is not a region where worlds bump into each other often. The Kuiper Belt is incredibly sparse compared to any earthly environment. The average separation between objects is millions of kilometers. Yet over the vast timescales of the solar system, subtle gravitational interactions have shaped their arrangement into distinct classes. Some KBOs, known as classical objects, have nearly circular orbits that have remained stable for billions of years. Others, the resonant objects, are locked into gravitational rhythms with Neptune. For example, Pluto completes 2 orbits for every 3 of Neptune's. Then there are the scattered disk objects, with stretched, tilted orbits that hint at violent past encounters, perhaps during the great planetary migrations in the solar system's youth. Each of these groups adds a layer to the Kuiper Belt's complexity, showing that this icy wilderness has a dynamic history. From a compositional standpoint, most KBOs are mixtures of rock and a variety of ices: water, methane, ammonia, and nitrogen. These substances would be gaseous closer to the Sun, but here, beyond the frost line, they have remained solid for over 4 billion years. In this way, the Kuiper Belt preserves the ingredients of the early solar system in a deep freeze, a cosmic pantry that nature never used up. Some objects, like Haumea, spin so rapidly that they are stretched into elongated forms, likely the result of a massive collision. Others are binary systems, where two similar-sized bodies orbit a common center of gravity. Pluto and its moon Charon are the most famous example, a double world locked in a slow, synchronized spin. Binaries may be common here, formed when two bodies drift close together and lose energy through gravitational interactions, becoming permanent partners. Size distribution in the Kuiper Belt follows a pattern. There are many more small objects than large ones, much like asteroid populations. But unlike the asteroid belt, the Kuiper Belt's objects are far better preserved, since the low collision rates and frigid environment have slowed erosion and change. In terms of mass, the Kuiper Belt contains only a small fraction of Earth's mass, likely between 1/25th and 1/10th of our Moon's mass in total. This is surprising given its vast volume, and it suggests that much of its original material was lost long ago, scattered inward or outward by migrating giant planets. What remains is a thinned but still intricate structure, a shadow of its youthful self. Discovering and studying these objects is a challenge. They are small, dark, and incredibly far away, reflecting only a tiny fraction of sunlight. Astronomers find them by patiently scanning wide areas of the sky, looking for faint points of light that shift slightly over hours or days. Each detection can take years to confirm, as orbital paths must be measured precisely to distinguish them from asteroids or distant comets. The known KBOs already reveal surprising diversity in surface features and histories. Pluto's nitrogen plains and towering ice mountains were unexpected in such a small, cold world. Arakoth's gentle contact binary structure suggests that not all bodies formed through violent impacts. These differences hint that even within this sea, local conditions and histories varied widely. The Kuiper Belt is also an active source for short-period comets, those with orbits lasting less than 200 years. When gravitational nudges or collisions send a small body inward, it begins to warm, releasing gas and dust to form the glowing coma and tail we see from Earth. In this way, the Kuiper Belt is connected to the inner solar system, sending icy messengers that remind us of the reservoir from which they came. Looking ahead, the coming decades promise a flood of new discoveries. The Vera C. Rubin Observatory, with its wide-field survey capabilities, will likely detect tens of thousands of new KBOs, including small ones that have so far escaped detection. Each discovery will help refine our models of how the belt formed and evolved, and perhaps reveal patterns that point to larger hidden influences, like the hypothetical Planet 9. In the grand architecture of the solar system, the Kuiper Belt is more than just an outer fringe. It is a sprawling, cold archive that holds the unedited record of planetary formation. Its countless frozen worlds, from lonely boulders to complex dwarf planets, embody the processes that shaped our cosmic neighborhood. Standing at the sun's edge, one would not see a crowded swarm, but a patient scattering of silent travelers, each tracing its own ancient path. Together, they form a slow-moving constellation, a reminder that even far from the warmth of the sun, the solar system is alive with worlds waiting to be known. Far beyond the orbits of the familiar planets, Neptune moves like a slow sentinel, its gravity extending an invisible hand into the dark frontier of the Kuiper Belt. This distant giant, pale blue and wrapped in swift winds, has shaped the outer solar system in ways we are only beginning to understand. Its pull is subtle but relentless, shepherding icy worlds into resonant orbits, capturing some while flinging others into exile. The Kuiper Belt, with its scattered disk of frozen bodies, is not just a chaotic graveyard. It's a structure carved by Neptune's quiet authority. Without this gravitational sculptor, the belt might have been a featureless cloud. Instead, it has order hidden in its apparent disorder, with patterns that trace back to the deep history of planetary migration. Billions of years ago, the solar system was not the stable arrangement we know today. The giant planets are believed to have formed closer to the Sun, embedded in a swirling disk of gas and icy debris. Neptune, smaller than Jupiter, but still massive, was not born where it now resides. It migrated outward over hundreds of millions of years, its gravity scattering small bodies ahead of it. Some of these icy fragments were trapped in orbital resonances, a kind of cosmic choreography, where a Kuiper Belt object completes a set number of orbits for every one of Neptune's. Pluto, for example, is in a 3-to-2 resonance, making 3 trips around the Sun for every 2 of Neptune's. This perfect rhythm ensures they never collide, even though their paths cross on a solar system map. The discovery of these resonances was one of the great revelations of modern planetary science. It told us that Neptune's role wasn't passive. It was actively shaping the belt into distinct zones. There are the Plutinos, sharing Pluto's resonance, the Totinos in a 2-to-1 resonance, and more distant bodies locked into slower rhythms. Between these resonant populations lie gaps, much like the empty lanes in Saturn's rings, cleared by the same gravitational principles. Just as Jupiter's gravity sculpts the asteroid belt, Neptune's influence sculpts the Kuiper Belt, a mirror of order imposed upon chaos, but Neptune's reach extends even farther. Some KBOs are detached entirely from its direct gravitational influence, sitting at such distances that their orbits cannot be explained by Neptune alone. These so-called detached objects, including the mysterious Sedna, have perihelia far beyond Neptune's pull. Their existence hints at deeper mysteries, perhaps a past encounter with a passing star, or the presence of an undiscovered massive planet lurking in the dark. Yet for the bulk of the belt, Neptune's gravity is the architect. This shaping wasn't instantaneous. During Neptune's migration, a vast number of small, icy bodies were scattered. Some were thrown inward to collide with the growing planets or be captured as irregular moons. Others were flung outward into the Oort cloud, the distant spherical shell that marks the solar system's boundary. The leftovers, those caught in just the right balance between escape and capture, became the Kuiper Belt we see today. In this way, Neptune didn't just sculpt the belt, it helped populate the solar system's outermost frontier. We can see Neptune's sculpting hand in the belt's orbital inclinations as well. Not all KBOs orbit neatly along the solar system's flat plane. Many have been tilted at steep angles, a sign of ancient gravitational encounters. This hot population contrasts with the cold, classical Kuiper Belt, where objects follow low inclination, near-circular orbits. The cold belt may be the remnant of the primordial disk, largely untouched, while the hot belt carries scars of Neptune's migration. This division gives planetary scientists a kind of fossil record, preserving evidence of the solar system's restless youth. Modern simulations support this picture. Computer models show that as Neptune migrated outward, it swept through resonances, capturing and releasing bodies along the way. These simulations reproduce many of the features we observe today, from the resonant populations to the scattered disk, but they also leave puzzles, unresolved. For example, why there are fewer resonant objects than models predict, or why the belt has such a sharp outer edge around 50 astronomical units. The answers may involve subtle gravitational interactions, collisions, or even the influence of bodies we haven't yet detected. Neptune's role in the Kuiper Belt's history also connects to larger questions about planetary systems in general. Observations of exoplanets show that migration is common. Giant planets often move from their birthplaces, reshaping their systems as they go. Our Kuiper Belt, shaped by Neptune's journey, may be a small-scale version of processes happening throughout the galaxy. In that sense, studying the belt isn't just about our own solar system, it's about understanding how worlds everywhere are arranged. Even today, Neptune continues to influence the Kuiper Belt. Every time a spacecraft ventures into the outer solar system, its trajectory must account for Neptune's pull. The same gravitational laws that guided Pluto into its safe resonance still operate, keeping the belt's architecture in balance. In the darkness beyond Neptune, icy worlds orbit with the quiet regularity imposed by their distant shepherd. And yet, there's something almost poetic about Neptune's influence. From our perspective on Earth, this planet is a faint blue dot, barely visible through a telescope. But in the vast darkness beyond, it is the silent ruler, shaping the lives of countless frozen worlds. The Kuiper Belt may seem wild and scattered, but its patterns whisper of an ancient dance, choreographed by a planet we can barely see. If we could watch the belt in time-lapse over billions of years, we would see Neptune's migration like a slow, sweeping hand, rearranging the pieces of a cosmic puzzle. Resonant worlds would settle into place like dancers finding their marks. Scattered bodies would drift into the deep or vanish into interstellar space. And in the aftermath, a belt of icy worlds, intricate, ordered, yet still mysterious, would remain. This is the legacy of Neptune's sculpting hand, etched into the farthest reaches of our planetary system. In the dim outskirts of the solar system, where sunlight arrives as little more than a whisper, a strange and unexpected beauty hides in the dark. The Kuiper Belt, long thought to be a loose scattering of frozen rocks and dwarf planets, has revealed a secret that challenges assumptions. Even some of its smallest bodies wear rings. For centuries, rings were the signature adornments of the gas giants, Saturn with its sweeping brilliance, Jupiter with its faint dusty arcs, Uranus and Neptune with their dark, narrow bands. But discoveries in the past decade have shown that this elegance is not reserved for planetary giants alone. In the icy silence beyond Neptune, small, irregular worlds also carry these delicate halos of debris, shimmering faintly against the black. The first real surprise came in 2013, when astronomers observed the distant Centaur object Chariklo passing in front of a star. This rare alignment, known as a stellar occultation, offered a chance to measure Chariklo's size and shape. But as the starlight dimmed and returned, researchers saw two brief dips in brightness before and after the main occultation. These were no random fluctuations. They were the signatures of narrow rings, two of them, circling a world barely 250 kilometers wide. The discovery was startling. How could such a small object hold onto rings? The finding forced scientists to rethink the conditions needed for ring systems to form and persist. Then, only a year later, another shock followed. Observations of the dwarf planet Haumea, a fast-spinning, elongated body in the Kuiper Belt, revealed it too was surrounded by a ring. Haumea's ring orbits along its equator, matching its rapid rotation period, and might be linked to a past collision that also created its two small moons. These back-to-back discoveries shattered the quiet assumption that rings were rare in the outer solar system's smaller realms. Instead, they hinted at a pattern. Rings might be more common than we ever guessed, even among worlds far from the sun's gravitational warmth. But what keeps these rings in place? Around massive planets, gravity is the obvious answer. The pull is strong enough to shepherd billions of icy particles into stable orbits. For small Kuiper Belt bodies, the situation is more delicate. Their gravity is weak, meaning ring particles could easily drift away or collapse onto the surface. The leading theories suggest that these rings may be relics of ancient impacts, where collisions shattered moons or surface layers, sending debris into orbit. Over time, these fragments spread into narrow bands, shaped and confined by small moonlets, shepherd moons, that may be too tiny for current telescopes to detect. Another intriguing possibility is that these rings are transient, lasting only millions of years. Brief flashes in geological time. If so, we may be catching these worlds in a special moment of their histories, before the debris settles or escapes. This could mean that many more Kuiper Belt bodies once had rings, their halos now lost to space. The rarity of our detections might not be because rings are uncommon, but because they're fleeting. Studying these rings is no easy task. The Kuiper Belt lies so far from Earth that even our most powerful telescopes struggle to resolve its smaller members. That's why stellar occultations, when a distant object passes in front of a background star, have become such powerful tools. The sharpness of the starlight's dimming can reveal not just the main body's silhouette, but any fine structures around it. Coordinated campaigns with telescopes spread across the world have allowed astronomers to detect rings around objects hundreds of times smaller than Saturn, turning each occultation into a potential discovery event. Rings in the Kuiper Belt also offer clues to the history of the solar system. If many of these bodies have rings, it could point to a more collision-rich past, where icy worlds frequently smashed into each other, releasing clouds of debris. The presence of rings around Haumea, which already shows signs of a violent history, strengthens this connection. It may be that the Kuiper Belt we see today is the quiet remnant of a once chaotic arena, where impacts were frequent and dramatic. There's also the question of composition. Unlike Saturn's bright icy rings, which are made mostly of water ice, the rings of Kuiper Belt objects may be darker, coated with complex organics formed by cosmic radiation over billions of years. This could make them harder to detect, especially against the faint glow of their parent bodies. Future missions, perhaps a spacecraft sent to a ring-bearing KBO, could directly sample or image this material, revealing the chemistry of the solar system's edge. The idea of small worlds wearing rings also invites us to reconsider what planetary beauty means. In the vast darkness beyond Neptune, far from the grand displays of Saturn, there are subtler spectacles, bands of dust and ice encircling worlds so small they could fit inside a single state on Earth. These rings may never shine as brightly as Saturn's, but in their rarity and fragility, they are perhaps even more precious. They are reminders that the solar system's elegance is not limited to the largest and most visible worlds, but is scattered throughout its farthest, coldest frontiers, and the discoveries may just be beginning. With new telescopes like the Vera C. Rubin Observatory set to scan the night sky with unprecedented depth, more stellar occultations will be recorded, more small worlds will be measured, and perhaps more rings will be revealed. If this happens, we might find that rings are not an exotic rarity, but a common chapter in the lives of Kuiper Belt bodies. In the end, rings in the dark speak to a universal truth about the solar system. Even in the most remote and seemingly barren places, there are patterns of beauty, physics, and history intertwined. They are silent records of collisions, migrations, and the delicate balance of gravity and motion. They tell us that the Kuiper Belt is not just a collection of frozen rocks drifting in the void. It is a dynamic, evolving realm where even the smallest worlds can carry the echoes of grandeur. In the frozen twilight of the Kuiper Belt, billions of icy bodies drift silently, locked in orbits that can last hundreds of years. To most, they remain unseen, too distant and dim to catch the eye, yet some of these wanderers are destined for a far more dramatic journey. Disturbed from their calm paths, they will begin a slow, spiraling fall toward the sun, transforming into something ancient observers feared and modern astronomers cherish: comets. Many of the short-period comets, those that complete a loop around the Sun in less than 200 years, can trace their origins to this remote region beyond Neptune, carrying with them frozen time capsules from the solar system's earliest days. When a comet approaches the Sun, it becomes a spectacle. A glowing coma forms around its nucleus, and a tail streams away, pushed by sunlight and the solar wind. But before this transformation, it exists as a small, inert world, a dark lump of rock and ice, stored for billions of years in the Kuiper Belt's cold storage. These objects, often only a few kilometers across, preserve the same ices and dust grains that existed when planets were still forming. Locked away in deep freeze, they have avoided the geological churning that reshaped the inner planets. In a sense, a comet's nucleus is a fragment of the solar system's childhood, carried into the present. The journey from the Kuiper Belt inward is rarely sudden. A comet might first be nudged by the gravitational influence of Neptune, its orbit subtly altered until it enters the region of the giant planets. There, repeated gravitational tugs, especially from Jupiter and Saturn, reshape its path, shrinking and rounding its orbit until it becomes a short-period visitor. This is why so many comets of the Jupiter family have orbital periods of less than a human lifetime. They are not ancient wanderers from the distant Oort cloud, but residents of the nearer, flatter Kuiper Belt, sent inward by a sequence of planetary encounters. The material these comets carry is among the most chemically primitive in the solar system. Analyses of comet dust, such as that collected by NASA's Stardust mission from Comet Wild 2, have revealed a surprising mix. Crystalline silicates that formed near the young Sun, and complex organic molecules that could only have formed in the deep freeze of interstellar space. This blend suggests a solar system in constant motion even during its birth, with material from near and far mixing before being locked into icy bodies. Each comet, then, is not just a frozen relic, but a record of ancient journeys that predate the planets themselves. The Kuiper Belt's role as a comet nursery is also a key piece in understanding Earth's own history. Some scientists argue that comets may have delivered a portion of our planet's water, as well as organic compounds that could have contributed to the emergence of life. Measurements of the ratio of heavy water with deuterium to normal water in certain comets have both supported and challenged this idea, suggesting that if comets did contribute to Earth's oceans, they were only part of the story. Still, their role as carriers of complex organics is undeniable, and the Kuiper Belt remains a vast, untapped reservoir of such material. The orbits of Kuiper Belt-borne comets often carry the fingerprints of their origin. Unlike the long-period comets of the Oort cloud, which swoop in from random angles, short-period comets generally move in the same direction as the planets, along the flattened plane of the solar system. This alignment is no accident. It reflects the disk-like shape of the Kuiper Belt itself, a structure inherited from the protoplanetary disk that birthed the Sun and planets over 4.5 billion years ago. Even after eons, the geometry of that ancient disk remains visible in the paths of these icy messengers. One of the most fascinating aspects of Kuiper Belt comets is how quickly they change once they enter the inner solar system. Repeated passes near the Sun cause their ices to sublimate and their surfaces to become coated in dark, insulating dust. In a few tens of thousands of years, a blink in cosmic terms, a once active comet can become dormant, its activity quenched, its appearance indistinguishable from an asteroid. In fact, many near-Earth asteroids may be the exhausted remains of former comets, their icy hearts long evaporated. Modern space missions have brought us closer to these visitors than ever before. ESA's Rosetta mission, which orbited and landed on comet 67P Churyumov-Gerasimenko, revealed a landscape of cliffs, boulders, and jets of gas, a world sculpted by both deep time and the sudden violence of solar heating. While 67P is a Jupiter family comet, likely, from the Kuiper Belt, the mission offered a rare glimpse of the kind of body that spends most of its life far beyond Neptune, untouched by warmth, until fate pulls it inward. Understanding the Kuiper Belt's contribution to the comet population is more than a matter of curiosity. Comets are natural probes of the outer solar system's composition, delivering material from beyond Neptune to a place where we can study it in detail. Each new comet observed, especially in the early stages of its inward migration, is an opportunity to read an untouched page of the solar system's story. With new wide-field surveys set to begin in the coming years, astronomers expect to discover many more short-period comets and trace their paths back to their icy origins. The next step in this exploration might even be a direct mission to a comet in its Kuiper Belt home. Such a journey would be difficult. The distances are vast, the sunlight faint, the travel times measured in decades. But the reward would be immense, a first-hand look at a body before the sun's heat ever alters it. In the untouched darkness we might find ices, organics, and minerals exactly as they formed billions of years ago, a living sample of the solar system's first moments. For now, each time a short-period comet sweeps across our skies, it is a reminder of the slow, patient work of gravity, the deep connections between the solar system's edge and its heart, from a frozen orbit beyond Pluto, through a winding path shaped by giant planets, to a bright arc near the Sun. These objects embody the solar system's capacity to link its most distant reaches with the worlds we know best. They carry the cold breath of the Kuiper Belt into the warmth of the inner planets, and in their brief, luminous lives, they let us touch the past. In the chill darkness far beyond Neptune, a small spacecraft drifts on a path no probe had ever taken before. New Horizons, launched in 2006, was designed to do something no other mission had attempted, to fly past Pluto and keep going, deeper into the frozen expanse of the Kuiper Belt. For 9.5 years, it raced through the solar system, crossing the orbits of the planets like milestones on a silent highway, until at last, in July 2015, it arrived at the most distant world ever explored. When New Horizons sent back its first close-up images of Pluto, the world was astonished. Far from being a dead, cratered ice ball, Pluto revealed a vibrant, complex landscape. Vast nitrogen plains smooth as glass, towering ice mountains as high as the Rockies, and a thin, layered atmosphere of blue haze. The heart-shaped plain, Sputnik Planitia, became an icon, a frozen basin likely formed by an ancient impact and then reshaped by ongoing glacial flows. Pluto's surface was not static, it was alive with slow-motion processes, reshaping the planet on timescales of millions of years. The encounter lasted only hours, but the data took more than a year to trickle back to Earth. The probe had flown within 12,500 kilometers of Pluto's surface, capturing details down to 80 meters per pixel. It revealed nitrogen ice cycling like water on Earth, exotic ices forming dunes, and dark equatorial regions stained with complex hydrocarbons. Even Pluto's 5 moons told a strange story. Charon with its colossal canyon systems, the tiny, fast-spinning moons Nix and Hydra, and the even smaller Kerberos and Styx, each a piece of an ancient collision between Pluto and another large Kuiper Belt object. But New Horizons' mission didn't end at Pluto. Using precious fuel for a carefully timed course correction, the spacecraft set its sights on a second target, a small, untouched Kuiper Belt body later named Arrokoth. Unlike Pluto, Arrokoth had never been significantly reshaped since the solar system's early days. It was a time capsule from 4.5 billion years ago, a piece of the original building, blocks from which planets formed. On January 1st, 2019, New Horizons flew past Arrokoth at a distance of just 3,500 kilometers, making it the most distant object ever visited by a spacecraft. The images that came back stunned scientists. Arrokoth was a contact binary, 2 lobes gently fused together, resembling a snowman flattened into an elongated shape. Its surface was smooth, lightly cratered, and painted in shades of reddish-brown from organic compounds called tholins. The very shape of Arrokoth told a story. It had formed not from a violent smash, but from a slow, graceful merger of 2 icy bodies, drifting together in the early solar system. This gentle history was a revelation. It suggested that at least some planetesimals, the seeds of planets, form not through high-speed collisions but through slow accretion within calm pockets of the protoplanetary disk. Such environments may have been common in the outer solar system, shaping the peaceful architecture of the Kuiper Belt we see today. Arrokoth's preserved state offered an almost direct glimpse into the solar system's nursery, frozen in time. Beyond the science, New Horizons became a symbol of exploration itself. Its journey showed that even the farthest worlds could be reached, that curiosity can carry human-made machines to places where sunlight is weak and the stars begin to crowd. The mission expanded the map of our solar system and gave personality to places once seen as faint smudges of light. Now, drifting ever outward, New Horizons continues to send back data on the environment of the Kuiper Belt, the distribution of dust, the glow of scattered sunlight, the properties of other distant objects glimpsed from afar. Its instruments still measure charged particles, plasma, and the faint whisper of the solar wind. Though its next close flyby target remains uncertain, it will keep traveling, past 50 astronomical units, 60 and beyond, until one day it crosses into interstellar space, joining Voyager and Pioneer on humanity's long reach into the galaxy. From Earth's surface, the Kuiper Belt remains a realm of icy mystery, but thanks to New Horizons, we have walked its edge in spirit. We have touched Pluto's nitrogen frost and seen the twin-lobed shadow of Arrokoth drifting in sunlight that left the sun 6 hours earlier. And as the probe sails onward into deeper darkness, it carries with it our first footsteps into a part of the solar system that, until recently, existed only in imagination. In the distant outskirts of our solar system, beyond the orbit of Neptune, the Kuiper Belt seems like a serene expanse of ice and silence. But this calm hides a restless history. the orbits of its frozen inhabitants, countless small worlds, from a few kilometers across to dwarf planets hundreds of kilometers wide, are not random. They are patterns carved and maintained by the invisible hand of a giant, Neptune. Over billions of years, Neptune's gravity has acted like a sculptor, shaping the Kuiper Belt structure, controlling its boundaries, and even deciding which objects can stay and which must leave. When the solar system formed, the giant planets were not where we find them today. In the earliest epoch, they likely orbited closer to the Sun, packed into a more compact arrangement. Beyond them lay a vast disk of icy planetesimals. According to the widely studied NICE model, interactions among Jupiter, Saturn, Uranus, and Neptune caused a dramatic rearrangement. As these giant worlds exchanged momentum, Neptune migrated outward, ploughing into the disk of icy debris. This migration was not gentle. It was a slow gravitational bulldozing that scattered countless bodies. Some were flung inward to become comets, others were cast out into the Oort cloud, and a fraction were trapped in stable orbital relationships with Neptune. These relationships are called orbital resonances, and they are among the most elegant patterns in planetary dynamics. In a resonance, a Kuiper Belt object, KBO, completes a set number of orbits for every orbit Neptune makes. Pluto is the most famous example, locked in a 3-to-2 resonance. It circles the Sun twice for every 3 Neptune orbits. Despite crossing Neptune's path in projection, Pluto never comes close to the giant planet, because their resonant timing ensures that when Pluto is near its closest point to the Sun, Neptune is far away. This gravitational choreography has preserved Pluto's orbit for billions of years. Resonances extend far beyond Pluto. There are KBOs in 2-to-1, 5-to-2, and even more exotic ratios with Neptune. These resonant populations form the dynamical skeleton of the Kuiper Belt, defining where objects can survive for the age of the solar system. Outside of these resonances lies the scattered disk, a population of icy worlds with highly elongated orbits. These bodies have been kicked into eccentric paths by past close encounters with Neptune. Some return near the giant planet's orbit at their closest approach, risking further scattering, while others have perihelia far enough away to remain stable for eons. Neptune also defines the Kuiper Belt's outer edge. Observations reveal a sharp drop in the number of objects beyond about 50 astronomical units, AU. This boundary, sometimes called the Kuiper Cliff, is thought to be a result of Neptune's past migration. As the planet moved outward, it destabilized the orbits of most objects beyond a certain range, ejecting them or trapping them into resonances that kept them closer in. The result is a belt with a surprisingly well-defined edge, almost as if Neptune had swept the region clean. Collisions also play a role in shaping the Kuiper Belt, though they are rare in the vastness of space. In the early days, when the belt was far more crowded, collisions between icy planetesimals were more frequent, grinding some down into smaller fragments and merging others into larger bodies. The debris from these ancient impacts still drifts in the belt, and some of it becomes the source material for short-period comets. Today, collisions are far less common, but over billions of years they can still subtly alter surface features, revealing fresh ice beneath weathered crusts. Evidence of Neptune's sculpting power can be seen in the cold and hot populations of KBOs. Cold classical objects have nearly circular flat orbits, suggesting they formed in place and avoided strong encounters with Neptune. They tend to have reddish colors and small sizes, indicating they are pristine remnants of the primordial disk. In contrast, hot classical objects have more inclined and eccentric orbits, likely stirred up by Neptune during its migration. These two populations live side by side, yet carry very different histories. One quiet and undisturbed, the other shaped by a turbulent past. The gravitational influence of Neptune doesn't end with the objects we can easily see. Some astronomers believe that the peculiar clustering of certain distant KBO orbits hints at the presence of an even more massive undiscovered planet, the hypothetical Planet 9. If such a world exists, its subtle pull could be adding another layer of complexity to the Kuiper Belt's orbital architecture. Whether or not Planet 9 is real, the fact remains. The region's current structure is a fossil record of planetary migration, gravitational interactions, and ancient chaos. In this way, Neptune acts both as a warden and an artist. It guards the belt's boundaries, removes unstable wanderers, and arranges the survivors into graceful resonant chains. Its past migrations were disruptive but also creative, turning a random disk of ice into a structured, multi-layered population of worlds. Without Neptune's guiding hand, the Kuiper Belt we know today, with its resonances, its cliff, its cold and hot classes, simply wouldn't exist. Even now, the story is ongoing. The solar system's outer edge is not frozen in time. Slow drifts, faint collisions, and the sun's distant pull all work in concert with Neptune's steady gravity. Over the next billion years, some KBOs will be nudged into unstable paths and flung away, while others will be drawn into new resonances. The ballet continues, unseen to the naked eye but recorded in the slow shifting of icy orbits against the backdrop of stars. The Kuiper Belt is not just a place, it is a dynamic testament to the solar system's restless youth. And at the heart of its shape, history and survival is the influence of a single planet, quietly sculpting from afar. In the frozen outskirts of the solar system, the Kuiper Belt stretches as a vast, diffuse halo beyond Neptune. Yet for all its breadth, it contains far less material than astronomers once expected. Models of planet formation suggest that the early solar system's outer disk should have been teeming with icy planetesimals, enough mass to build planets many times the size of Earth. Instead, the Kuiper Belt today contains perhaps only 0.1% of Earth's mass. This discrepancy, the missing mass problem, has puzzled scientists for decades and challenges our understanding of how the solar system evolved. When astronomers first recognized the Kuiper Belt's existence in the 1990s, they imagined it as the leftover remnant of the primordial disk. In those early simulations, billions of kilometers from the Sun, small icy objects coalesced slowly from dust and gas. With time, collisions and mergers should have built bodies hundreds or even thousands of kilometers wide, and the total mass in this region might have been 10 to 100 times what it is now. Yet the first surveys found a surprisingly sparse population. Even factoring in unseen objects too small or too distant for detection, the numbers still fell far short. One possible explanation lies in the violence of the giant planet's migration. If Neptune and Uranus formed closer to the Sun and moved outward, they would have scattered enormous numbers of icy planetesimals into interstellar space, or the distant Oort cloud. The NICE model suggests that during this migration, much of the Kuiper Belt's original mass was ejected, leaving only a thin fraction behind in stable orbits. This scenario fits with the observation that many Kuiper Belt objects, KBOs, have highly inclined and eccentric orbits, as if tossed about by past gravitational upheavals. Another possibility is that the Kuiper Belt began to lose mass even before Neptune's arrival. As the young Sun ignited, its intense solar wind and ultraviolet radiation could have stripped lighter, smaller particles from the outer disk, especially the fine dust that would otherwise have helped planetesimals grow. With less building material, growth rates would have been slow, and collisions might have been more likely to shatter bodies than merge them. Over hundreds of millions of years, repeated impacts could grind much of the mass down into fragments, small enough to be blown out of the solar system entirely. The missing mass problem also hints at differences in accretion efficiency. Nearer to the Sun, where densities were higher, planetesimals could merge quickly into large planets. But at the distances of the Kuiper Belt, orbital speeds are slower and encounter rates lower. This means it may never have been easy to assemble massive bodies there, and the few large dwarf planets we see today might be the rare survivors of an inefficient process, not the typical outcome. Observations from the New Horizons mission and deep sky surveys have refined these estimates. By studying the number and size distribution of KBOs, astronomers have concluded that the total current mass of the Kuiper Belt is likely only 0.01 to 0.1 Earth masses. This is strikingly small compared to the expected primordial disk mass needed to form the giant planets themselves, suggesting that over 99% of the material has been removed. The question then shifts from why is it light to where did it all go? Some of that mass may have been delivered inward. Scattered planetesimals could have bombarded the inner planets in the late heavy bombardment, delivering water and volatiles to Earth and Mars. Others may have escaped the sun's pull entirely, becoming interstellar wanderers like the object Oumuamua, which may be a relic of a distant system's own planetesimal belt. Still others might linger unseen in the far-flung Oort cloud, invisible to our current telescopes. There is also the intriguing possibility that the Kuiper Belt structure hides its history. The cold classical population, objects with low inclinations and nearly circular orbits, seems largely untouched since formation, yet contains far too little mass to match models. This suggests that depletion was a system-wide event, not just a side effect of scattering near Neptune. Even the most stable regions were somehow robbed of their mass, hinting at processes we do not yet fully understand. The mystery of the missing mass remains unsolved, but it is a critical clue to the solar system's past. Each theory, giant planet migration, collisional grinding, solar radiation blow-off, inefficient accretion, explains part of the picture, but not all. The truth may be a combination of all these factors, layered across hundreds of millions of years of change. As new surveys push deeper into the Kuiper Belt and telescopes like the Vera C. Rubin Observatory begin scanning the sky, we may finally fill in the details. Until then, the Kuiper Belt stands as both a relic and a riddle, a reminder that the solar system we see today is only the thinnest remnant of the bustling, massive disk from which it was born. The rest is gone, scattered to the dark. Far beyond Neptune, where the sun's warmth fades into the deep cold, astronomers have found orbits that do not quite make sense. A handful of distant Kuiper Belt objects, KBOs, share peculiar alignments. Their elongated paths tilt and cluster in ways that should quickly disperse if only Neptune's gravity were in play. This strange choreography has inspired one of the most intriguing ideas in modern planetary science: the existence of a massive, unseen world, perhaps 10 times the mass of Earth, shepherding these objects from the shadows. They call it Planet 9. The story began in the early 2010s, when careful mapping of extreme trans-Neptunian objects revealed a pattern. Instead of being randomly oriented, many had perihelia, the closest point in their orbits to the Sun, grouped in the same direction. Their orbital planes also tilted similarly, as if twisted by the same invisible hand. At such distances, Neptune's influence weakens, and the galactic tide, the subtle tug of the Milky Way, should only cause slow, random drifting. The persistence of the alignment hinted at a gravitational anchor. In 2016, astronomers Konstantin Batygin and Mike Brown published a bold hypothesis. A ninth planet, far larger than Earth but smaller than Neptune, could explain the data. Their models suggested it would orbit the Sun at an average distance of perhaps 400 to 800 astronomical units, taking 10,000 to 20,000 years to complete a circuit. This world would be a frozen giant, a relic of the solar system's youth, perhaps scattered outward during the giant planet's early migrations. Its gravity, spread over vast distances, could maintain the clustering of extreme KBOs and even explain other anomalies, like unusual tilts in the orbits of some distant objects and the Sun's slight axial misalignment. The Planet 9 idea gained attention because it elegantly tied together multiple puzzles. It could account for Sedna's strange path, which never approaches Neptune closely enough to have been shaped by it. It could also explain why some KBOs are pushed into orbits perpendicular to the plane of the solar system. Models without Planet 9 struggle to reproduce these features without invoking rare coincidences or untested physics. Yet, despite years of targeted searches with some of the world's most powerful telescopes, Planet 9 remains unseen. Its predicted position covers a vast swath of sky, and if it lies near the farthest part of its orbit, it would be extremely faint, dimmer than the smallest dwarf planets we have spotted so far. Surveys must balance deep imaging with wide coverage, a challenge when the sky is full of faint background stars and galaxies. Skeptics point out that observational bias could mimic the clustering. Extreme KBOs are rare and hard to find, and our surveys have not been uniform. It is possible that the alignment is an illusion caused by where astronomers have looked. As more objects are discovered, some of the clustering has loosened, though not enough to erase the mystery entirely. If Planet 9 exists, its origin is another question. It might be a rogue giant planet flung outward from the inner solar system during chaotic early encounters, where it settled into a distant, elongated orbit. Alternatively, it could be a captured planet from another star, a rare but possible event during the Sun's birth in a dense stellar nursery. Its mass and composition could resemble a scaled-down ice giant, with a dense core and thick mantle of ices under a frigid atmosphere. The search for Planet 9 has also sharpened our tools for exploring the deep solar system. Automated surveys now scan larger areas with greater sensitivity, detecting new distant worlds and refining orbital maps. Each discovery adds to the statistical weight of the case, or challenges it. The upcoming Vera C. Rubin Observatory, with its sweeping all-sky survey, may provide the decisive evidence within the next decade, either revealing Planet 9 as a faint moving point of light or ruling out its most likely parameters. Even if Planet 9 proves elusive, the investigation has already transformed our view of the outer solar system. It has shown that we have not yet finished mapping our own planetary neighborhood, and that unseen forces, whether a hidden planet or subtle gravitational effects, continue to shape the architecture beyond Neptune. The Kuiper Belt, scattered disk, and possible inner Oort cloud remain frontier territory, holding secrets that remind us how incomplete our picture still is. Some astronomers have drawn parallels between the hunt for Planet 9 and the 19th century search for Neptune itself, predicted from the wobbles in Uranus's orbit before it was seen. But history also offers caution. Not every anomaly signals a new planet. Sometimes the answer lies in refining our measurements, not expanding our census. For now, the mystery persists, a whisper of something massive, patient and hidden, looping slowly in the cold night at the edge of the sun's reach. At the far edge of the Kuiper Belt, the sun is little more than the brightest star in a black sky. Here, the solar system does not end abruptly. It fades. The familiar disk of planets, moons, and icy debris begins to dissolve into a vast, unseen sphere that surrounds us on all sides. This is the gateway to the Oort cloud, a realm so distant that even our fastest spacecraft will not reach it for tens of thousands of years. The Kuiper Belt, though remote, is still a structured region. Its members travel in relatively flat, stable orbits influenced by Neptune's gravity. But as we move farther out, the sun's grip weakens. The objects here, sometimes called scattered disk objects, follow elongated, tilted paths, many pulled into strange trajectories by ancient gravitational nudges from passing stars or the tidal forces of the Milky Way itself. This gradual scattering is a bridge between the organized geometry of the Kuiper Belt and the isotropic chaos of the Oort cloud. The Oort cloud is not directly observed. It is inferred from the behavior of long-period comets, which arrive from every direction, their orbits unbound to the solar system's flat plane. To explain this, astronomers propose a nearly spherical shell of icy bodies, extending perhaps halfway to the nearest star. The inner Oort cloud may begin around 2,000 astronomical units from the Sun. The outer edge could lie at 100,000 astronomical units or more. Within it, trillions of icy fragments, leftovers from the solar system's formation, drift in darkness, disturbed only occasionally by a passing star or galactic tide. The transition between the Kuiper Belt and the Oort cloud is not a sharp line. Imagine a dim, cosmic shoreline where the last islands of the Kuiper Belt rise from a sea of scattered ice. Beyond these, orbits grow so eccentric that objects spend most of their time far from the Sun, returning only briefly over millions of years. Some, like Sedna, are believed to inhabit this transitional zone, too far to be Kuiper Belt members, too bound to be part of the outer Oort cloud. Their existence hints at past encounters with other stars during the Sun's youth, when its birth cluster may have stirred these icy remnants into distant orbits. In the Oort cloud's vast emptiness, the Sun is not the dominant source of light. The galaxy itself, with its billions of stars, forms a faint collective glow. Temperatures hover just above absolute zero, preserving primordial material from 4.6 billion years ago. If we could hold a piece of Oort cloud ice in our hands, we might see the same composition that existed before Earth had oceans, continents, or life. These are the time capsules of the solar system, carrying ancient water, carbon compounds, and perhaps the seeds of life itself. Every so often, a gravitational disturbance jolts one of these frozen bodies onto a path toward the inner solar system. As it approaches the sun, heat awakens it, sublimating ice into brilliant tails, the comets we see from Earth. In this way, the Oort cloud remains connected to our skies, sending us messengers from a realm we cannot visit. For spacecraft, crossing into the Oort cloud would mark entry into true interstellar space, where the sun's influence yields almost entirely to that of the galaxy. Voyager 1 and 2, though now in interstellar plasma, will not reach the inner Oort cloud for thousands of years. This emphasizes its scale. It is not just far away, it is unimaginably vast. The fading into the Oort cloud is a reminder that our solar system is not an isolated bubble, but part of a larger galactic ecosystem. The icy bodies at its edge may have siblings orbiting other stars, and their histories may be linked through past stellar encounters. In a way, the Oort cloud is both the solar system's outer wall and its handshake with the galaxy, a place where our sun's family of worlds blends into the shared drift of the Milky Way. At the very edge of the sun's dominion, there is no wall, no sudden boundary, only a slow unraveling of certainty. The planets, their moons, and the smaller icy bodies of the Kuiper Belt still orbit with a sense of belonging, tethered to the sun by the faint pull of gravity. But here, at the solar system's frontier, that tether begins to fray. Beyond this region, our star's influence fades into the quiet drift of the galaxy, and the space between worlds becomes so vast that it feels like the beginning of somewhere else entirely. The Kuiper Belt is not merely an outpost of ice, it is a threshold. On one side lies the ordered architecture of our planetary system, a cosmic neighborhood shaped by billions of years of gravitational negotiations. On the other side stretches the realm where the sun must share its authority with the galaxy at large, a domain where passing stars, molecular clouds, and the slow tide of the Milky Way compete for influence over scattered, frozen remnants. This is the sun's last frontier, and crossing it means stepping into interstellar space. The sun's gravitational reach technically extends far beyond the Kuiper Belt, even beyond the distant Oort cloud. In theory, it stretches for light years before fading completely into the gravitational field of other stars. Yet, in practice, the edge of the Kuiper Belt is where the solar system's structure gives way to a more chaotic scattering of objects. Here, the neat orbital plane begins to dissolve, and the icy bodies travel on elongated, tilted paths, hinting at past disturbances and the ongoing touch of the galaxy. Voyager 1 and Voyager 2, humanity's farthest emissaries, have already crossed the heliopause, where the solar wind yields to the interstellar medium. But even these spacecraft are still deep within the sun's gravitational domain. Their journeys remind us that leaving the solar system is not a moment but a process, one that takes tens of thousands of years to complete. The Kuiper Belt marks the first major step in that journey, a place where our star's warmth is almost gone, but its memory still lingers in the icy cores of ancient worlds. Standing here, in thought, the sun is no longer a blazing disk. It is a bright point, the way other stars look from Earth. Its light takes hours to reach this far, and shadows are long, soft, and cold. The heat is not enough to melt surface ice. Even volatile gases remain frozen solid. The planets we know, Jupiter, Saturn, Uranus, Neptune, are lost in the distance, indistinguishable from background stars without a telescope. This is a vantage point where the solar system is no longer something you are inside of, but something you can see as a whole, suspended in the dark. The Kuiper Belt's edge also carries with it a story of beginnings. The ice and rock here are leftovers from the solar system's birth, fragments that never coalesced into planets because they formed too far from the sun's warmth. They are time capsules, preserving the chemistry of the early solar nebula. Studying them, whether with distant spacecraft like New Horizons or through the rare comets that journey inward, gives us glimpses of our origins, and in turn, they whisper of endings, the eventual fading of the sun's light, and the idea that someday these objects will orbit a star that no longer shines. Beyond this frontier, the solar system's story begins to merge with the galaxies. The forces that shape these distant bodies are no longer solely solar. Passing stars can tug them into new paths. Giant molecular clouds can scatter them like leaves in wind. Even the slow gravitational tide of the Milky Way can nudge them toward the inner system, where they might appear as long-period comets. The Kuiper Belt is thus not just the end of our system, it is also a meeting place, a zone of exchange between our Sun and the wider universe. In the vast stillness here, there is a paradox. This edge is both a boundary and an invitation. It reminds us that our solar system is finite, a small island in an endless ocean, yet it also shows us a path outward. The same gravitational bonds that hold the Kuiper Belt together are the ones that, when loosened, can send its icy messengers across interstellar space, perhaps even to seed life elsewhere. For now, we have only begun to explore this realm. The New Horizons spacecraft has shown us that even the smallest, coldest bodies here can be rich in complexity, with layered histories, strange shapes and surface features sculpted by processes we do not yet fully understand. Future missions may push deeper, tracing the slow fade of the solar system into the Oort cloud, and eventually into the galaxy itself. The last frontier of our Sun is not just a place, it is a perspective. From here, you can see the solar system for what it truly is, a temporary arrangement of matter around a single star, bound together by gravity for a finite time. The Kuiper Belt is its boundary marker, a reminder that beyond the reach of familiar planets lies the unknown, waiting. And in that unknown lies the continuation of our story, one that will outlive the Sun itself. The Kuiper Belt is not a chaotic scattering of debris. It's an elegant dance, choreographed by gravity and time. Many of these icy worlds are locked in orbital resonances with Neptune, completing their journeys in perfect mathematical harmony. Pluto circles the Sun twice for every 3 orbits Neptune makes, a cosmic waltz that has continued for billions of years. Some objects spin so rapidly they've stretched into elongated shapes like cosmic footballs tumbling through space. Others travel in pairs, binary worlds locked in their own intimate dance, orbiting each other as they journey around the Sun together. Perhaps most beautifully, the Kuiper Belt isn't isolated from our world. It sends us messengers, comets that begin their journey in this frozen realm and spiral inward toward the Sun. When we see a comet's glowing tail streaking across our night sky, we're witnessing a piece of the Kuiper Belt visiting our neighborhood, carrying with it the same ice and dust that existed when Earth was young. These ancient travelers bring us samples from the solar system's birth, frozen time capsules that have remained unchanged for over 4 billion years. In their chemical signatures, we read the story of how worlds are born. As we drift here in thought, at the edge of the Sun's domain, we realize something profound. The Kuiper Belt is both an ending and a beginning. It marks the boundary of our planetary neighborhood, yet it also points the way to something greater, the galaxy beyond. Future missions will venture deeper into this realm, perhaps visiting worlds we can barely see today. With each discovery, each photograph sent back across billions of kilometers, we add new chapters to the story of our cosmic home. The Kuiper Belt reminds us that our solar system is far stranger, far more beautiful, and far more vast than we ever imagined. In its frozen silence, countless worlds wait patiently in the dark, each one a universe of possibilities. So tonight, as you drift towards sleep, remember that beyond Pluto, beyond the reach of the Sun's warmth, an entire civilization of ice and rock continues its eternal journey through the cosmos. They are the guardians of our solar system's edge, the keepers of its deepest secrets, and the silent witnesses to 4.5 billion years of cosmic history. Sweet dreams, fellow travelers. The universe is vast, mysterious, and more wonderful than we dare to dream.